This is going to be the lecture over section 28.6. We're going to look at the wave nature of particles. So just as photons have a wavelength of lambda is equal to Planck's constant divided by the momentum, using this relationship, which we've known for quite some time, and this equation gives the de Broglie wavelength for a particle of mass m of this. So basically we're changing out the momentum for the mass times the velocity. So an essential concept of quantum mechanics is that the particle is no longer described as located at a single point, but is instead an inherently spread out entity. Electrons within atoms can be visualized as diffuse clouds surrounding the nucleus. So this is, we're getting into some quantum stuff here. So some aspects of the emission and absorption of light can be understood on the basis of photons and atomic energy levels. But if we're looking for a complete theory, it should be able to offer some means of predicting these values of energy levels for any particular atom. The Bohr model was a start, but it cannot be generalized. So for more general problems, even more sweeping revisions of the 19th century ideas are going to be needed. So the wave-particle duality of electromagnetic radiation has to be extended to include particles as well as radiation. As a consequence, a particle can no longer be described as a single point in space. Instead, it is an inherently spread out entity. As a particle moves, its spread out character has some of the properties of a wave. The new theory, quantum mechanics, is key to understanding the structure of atoms and molecules, including their spectra, chemical behavior, and other properties. It has the happy effect of restoring unity to our description of both particles and radiation, and wave concepts are a central theme. So the major advance in the understanding of atomic structure began in 1924 with a proposition made by a young French physicist, Louis de Broglie. His reasoning, freely paraphrased, went like this: nature loves symmetry. So if light is dualistic in nature, in other words, it behaves like a wave, and in others like a particle, if nature is symmetric, this duality should also hold for matter. Electrons and protons, which we usually think of as particles, may in some situations behave like waves, and believe it or not, he got a doctorate just basically off of that simple concept. So, an application here, boron neutron capture theory. If particles exhibit wave-like behavior and the wavelength and energy of a particle depend on its velocity and mass, experimental form of brain cancer therapy uses beams of slow-moving neutrons called thermal neutrons that are the proper wavelength. They have just the right amount of energy to be absorbed by boron atoms, which are then converted into an unstable state. These unstable boron atoms then split into high-energy lithium nuclei and alpha particles that are deadly to nearby tissue. But because they can travel only a few micrometers, or micrometers, less than the width of a human cell, they will kill only the cell that has contained the boron atom. Medical researchers have developed boron-containing compounds that are selectively taken up by tumor cells, ensuring that only tumor cells will be destroyed with a beam of thermal neutrons. So, this comes, the de Broglie wavelength here basically comes from the relationship that we have here, that momentum is going to be equal to the Planck's constant divided by the wavelength. This is just a readjustment of that. The wavelength of macroscopic objects such as a bullet or a baseball are much too small to be measured. And situations like this, basically at a macroscopic level, like what we observe, we're not going to see, or these types of relationships should reduce down to the classical formulations that we've come to know. So, the dual nature of the electromagnetic radiation has led to the adoption of the photon concept. A similar revolution was needed in mechanics of particles. So an essential concept is that a particle is no longer described as located at a single point, but is instead an inherently spread out entity described in terms of a function that has various values at various points in space. So the spatial distribution describing a free electron has a recurring pattern characteristic of a wave that propagates through space. This suggests how a wave function for a free electron might look. The wave is more or less localized in space. Now, if you don't look too closely, it looks like a point particle, but it clearly has wave properties, including indefinite wavelength. So basically, it's got wave and particle properties. So yes, this is an electron. Weird, wacky, wild stuff.